Hello everyone, welcome to the presentation of our ISEC-FSC 2021 paper. I am Suman Biswas. I am a computer science PhD candidate at Iowa State University. My supervisor is Professor Ridesh Rajan. I am going to talk about fair preprocessing towards understanding compositional fairness of data transformers in machine learning pipeline. Alright, so let's talk about what is fairness in software. Firstly, we have a continuous effort to eliminate social discrimination. People should not get advantage or disadvantage because of their protected attributes like race, sex, or age. However, our decision-making software can encode biases systematically. Certain people can get systematic privilege in loan approval or hiring employees or criminal sentencing. Here we are focusing on such algorithmic fairness of machine learning software. The goal is to identify unfairness and then make it fairer. Recently, we experienced many of these fairness violations. Minority people receive biased decisions. Facial recognition and automated pricing favored some people than others. Even in crime prediction of courts, the predictions have been shown to be violated. So, software requirements have been also evolving over the times. With the functionality, we have to ensure the fairness as well. In software engineering research, we study defects of bugs which violate these requirements. We localize and test and fix these problems. We envision fairness as a similar issue in software engineering, which also needs to be addressed with respect to all this. Fairness testing has been studied in the last couple of years by the community, but we need further tools, methods, and languages to focus more on these activities. Well, what challenges lie in identifying fairness in machine learning software? Firstly, in ML, we learn from data. So, if the data itself is biased, our software would be unfair. Secondly, ML software is more of a black box with complex structure and it's hard to reason. Many of the prior work actually proposed fairness metrics to identify and measure unfairness, but they consider fairness of the ML pipeline holistically and do not actually consider the fairness of the components. I'm going to explain this in a little bit. So this is what a machine learning pipeline looks like. The training data goes through a set of pre-processing stages before feeding it to the ML classifier. Then the trained model operates on the test data to make prediction. So what are these stages? It can be missing value removal or data encoding or maybe normalizing. Sometimes a subset of feature or example are selected by sampling. Finally, and the model is built by the classifiers such as decision tree, support vectors, and so on. Previously, fairness has always been evaluated in the end for the ultimate prediction. We don't know the fairness of these data transformers. Are they contributing to the fairness of the outcome? We collected actually data transformers which are well-known algorithms such as PCA or SMOT from the libraries. Also, some custom pre-processing stages like new feature creation or missing value removal. Here is a simple example. The developer builds the ML classifier using Compass data for predicting future crime. First, the developer performs custom data filtration. Then some imputation is done on missing values. Then another feature imputation is done on a different feature, followed by binarizing the variable. Finally, a logistic regression classifier is trained on the process data. The existing metrics show that final outcome is biased toward Caucasian defendants. But what is the fairness of these pre-processing stages? Are they fair? If yes, then how much? Therefore, in this paper, we proposed a method to evaluate fairness of the stage SK. Specifically, a stage SK operates on the data already processed by the previous stages. We used actually causal reasoning to identify the prediction discrepancy made by the specific stage. Next, I'm going to talk about that. Identifying causal effects has been actually integral part of scientific inquiry for a long time. It helped to answer wide range of questions like effect of social policies or risk factors of diseases and so on. For example, in software engineering, causal testing is widely used. Given a failing test, we experiment with a set of test passing inputs that are very close to the failing input in order to find some bugs which is causing the program to fail. In this paper, we also used the causal modeling proposed by Pearl. We intervened on one variable of interest at a time and observed the changes Causality in fairness has also been studied in the literature, like to find whether the age of the people is affecting credit approval or not by mutating the actual age. Galhotra et al. Used this method to propose fairness testing. They mutated the protected attribute by keeping the other features the same. Does this change the prediction? If yes, then it's unfair. And what we did is that we made intervention on the system, not on the inputs, to observe causal effects of the preprocessing stages in the pipeline. Our formulation looks like this. We create an alternative pipeline P star from the given pipeline P by actually removing the preprocessing stage in consideration, which is SK in this case. In some cases, the stage cannot be removed. In that case, we replace it with another stage, that is the base stage. Then we look at the prediction disparity, which is y of p and p star, that is captured by the impact set I. The disparity can be fairness satisfying or not. To evaluate that, we used some existing fairness criteria M here to measure whether the stage SK is fair in the pipeline P. Here is the new stage specific fairness metric that we proposed. For example, based on the fairness criteria in statistical parity, we create the metric SF-SPD. Similar to SPD, we also used three other fairness criteria and that are equal opportunity, average odd difference, and error rate difference to propose these four noble metrics. We conducted a thorough evaluation on the benchmark of 37 ML pipelines and 69 preprocessing stages. The pipelines are collected from these three different sources. Those are essentially real-world pipelines collected from Kaggle, some previous work in the area, and the pipeline operates on 5 different datasets. The experiments are designed to collect the information needed to compute those 4 metrics. First, the alternative pipeline is created from the original, which captures the causality. Second, after the training, the impact set is computed from the disparity between YP and YP star. Finally, using the different fairness criteria, we measure the fairness of the stage SK. We answered these 3 research questions in our paper. First, what are the fairness measure of the preprocessing stages? And secondly, among popular data transformers from libraries, which are fair or unfair? And third, how does the stage-specific metrics actually compose, and whether the composition helps us to choose appropriate data transformers. Here are a few key findings from our evaluation. We found that real datasets often contain missing values. The pipelines use different imputation techniques like replacing with most frequent values. Although this method might help the accuracy, we found these worsen the fairness. The size of the bars here represent the amount of unfairness. Positive values do not bias towards unprivileged and negative values do not bias towards privileged. Another popular data preprocessing category is sampling. Developers use algorithms like SMOT or AllKNN to over or undersample the data. These techniques show a great deal of unfairness. However, we found that we can actually use the fairness composition of multiple unfair stages to mitigate the overall bias. Especially in RQ3, we showed that the local fairness, which is basically fairness of the stage, contributes to the global fairness. To illustrate this further, suppose in this pipeline, these 2 red stages are biased toward group A, such as male, that is making the whole pipeline unfair. Now, what if we replace this one with another biased stage that is biased toward group B, such as female? Our case study shows that based on our stage specific evaluation, we can instrument the pipeline to mitigate bias. Here, the undersampling method shows bias, which has been mitigated by another stage that is scaling the features. This shows future prospect to both localize unfairness in the pipeline and fix that by instrumentation. To finish with, I will be on the job market this academic year. Broadly, my research interest is in the intersection of AC, PL, and data science. So feel free to contact. Thanks a lot for attending the presentation. Our paper looks inside the black box of ML pipeline and locate unfairness issues in different components. You can get the accepted artifact from the GitHub repo and the preprint from the archive. Thanks again.